topic, we're looking at the solution of the continuous time state equation. So we have the state model in continuous time, x dot, the derivative of x is equal to ax plus bu, y is equal to cx plus du. So we have a matrix differential equation. We have initial condition, well actually this is the vector differential equation. So this is a vector, and we have in general, we may have multiple inputs, multiple outputs. And so as in the discrete time problem, we have the question of what does the state mean, what does the state transition matrix do, and what does the response look like? Those are the similar questions to what we looked at, in fact, they're the same questions in the discrete time. Again, the concept of state is that even though the system may be doing something up till time t0, from time t0 on, the response depends only upon the condition at time t0 and the input from that point on. It's not dependent on the input, for example, in the past time. It's only dependent upon the state. The input has brought the system to a particular state. Once we have that state, it doesn't matter what the input was before then. Knowing that state is enough to tell us what's happening from that point on. In the simple case, as simple as it gets, is when x dot is equal to ax plus bu. This is the linear time invariant case where we have some initial condition t naught, x at t naught, and the solution to the differential equation is given by this expression. X of t is equal to e to the a t minus t naught x to t naught, the integral from t naught to t of e to the a t minus tau b u of tau d tau. And so this is the solution to this differential equation. So as in the discrete time problem, we had the natural response, that is the response to the initial condition, and then we had the forced response. This is the response due to the input. We see also here that the response due to the input is a convolution. In this case, it's a continuous time convolution integral. So we have that. Instead of having a to the k or a to the t, as in the discrete time, we now have e to the at, where the e to the at is the matrix exponential, and it can be expressed in a power series this way. So we have this power series where a squared stands for a times a cubed, a times a, and so forth. So this is an infinite series in a matrix infinite series. So this e to the at, as we can see, appears in here in a couple of different places, and it's significant because it shows that the system is obviously affected by a, but it does so in an exponential kind of way. So the matrix exponential is a very significant matrix, and it has quite a number of properties. So here are a list of properties for the matrix exponential. So e to the 0, if we have a zero matrix, is the identity. So we can kind of see that here, for example, if t is 0 or a is 0, then all of these terms go away and we're just left with the identity. So some of these are really easy to prove. Some of these properties are very easy to prove, others not so much. We'll prove a couple of them in the proofs video for this lecture. E to the a t, e to the a tau, I can combine these two exponentials into a single exponential and sum the arguments. So if I let tau equal t or minus t, then this is the situation that I have, in which case I have e to the 0, which gives me the identity. So this property actually leads to this property here, that the inverse of e to the at is e to the minus at. Right? So those two properties are the same. Similarly, if I have two matrices, A and B, I can combine them in the exponential if the two matrices commute. If the two matrices do not commute, then in general these two will not be equal to each other. So there's an unusual thing associated with the matrices commuting or not. If I take the similarity transformation of e to the at, that's the same as taking e to the similarity transformation of a times t. So again, there's that's for t non-zero. If I take the matrix exponential of A transpose, that's the same as taking the matrix exponential of A and then transposing the result. Also, A times e to the at is equal to e to the at times A. That is, they commute. A commutes with e to the at. So I can multiply. So in general, matrices do not commute, but in this case, these matrices do commute. And finally, the derivative with respect to t of e to the at is a e to the at. Okay, so we actually have this result. So, properties of the matrix exponential and the solution of the continuous time case. So, the solution, as we can see, is fairly complicated, and so I have reserved the proof for the proofs video because it is fairly complicated.